Hi, Michael. Is your first name pronounced perfectly?
Yes, that's the formal one, but Michalis is the most casual thing. It's like Mike and
Michal?
Michael. Michalis.
Michalis. Okay.
Yes, exactly. So it's like
Michalis.
Michael and Mike. So yeah,
Ah, okay. Michalis.
yeah,
Um, okay. What was your first computer?
yeah. So I think it was back in 1997. I had a Pentium 2 with a big CRT screen. I think that's the first memory that I have from a computer back then.
133 megahertz, I guess, right?
Think it should be more than that. I think it was about in the between 200 and 300 back then. But
Net
yeah,
2, Pentium 2, you're right. Pentium 1 was started, I think, with 60, 90, 133, and the Pentium 2 is more than that, so already 233. Almost a quarter of a
yeah,
gigahertz, right?
exactly. Yeah.
And what you did with the computer?
To be honest, the first thing that I remember doing, I was playing Doom 2. I think that was the thing, the main thing that I was playing. Yeah, I was playing Doom back
So
then, and
immediately install Doom.
I think someone else. I think my uncle, he was the computer guy, so he had installed the Doom 2. I think that was the first game I remember playing that computer
Mhm.
and doing things in Paint because back then I was 4 years old. So
Mhm.
that's the first memory that I have is Doom and Paint. So okay, it's a bit contradictory memory, but yeah.
So you like Paint?
No, but at this point, at this age, you didn't have too many choices. So either playing games or paint something back then. So
Mhm. And when you started to do something more serious, not just playing rather than
yeah,
scripting, whatever.
well, for me, coding came much later. So I didn't have any, interaction with coding until university. So until I got 18 and I start studying at the university, it was my first proper coding experience. So up to that age, I didn't have, maybe I played a bit with some educational tools uh, to do some pseudo coding when I was in high school, but that was it.
Mhm.
Yeah.
Okay. And what was your first, or when you were forced to do something? You said at the university.
So yes, when I was a first year undergraduate, my first interaction with coding was with Java, actually. So it was with a book that was called Objects First with Java,
Oh,
and it
really?
was yes.
But the question: if you just played, so how you got to programming? So you were interested in computers. How you knew that you would like to do something with computers?
Well, I was in more, mechanical side of things. So I was the kind of the kid that I was had always a screwdriver in my hand. I would try to, take apart my computer, switch the GPU, try to take everything out and reinstall it. I would try to format my computer without any reason, but never programming. So I was curious of reassembling things and doing this kind of more engineering stuff when I was younger. So when I moved to the university, programming came a bit natural of
Mhm.
this
But you
from this.
never tried before. You
No, just I think in high school I was in Greece, so we had uh, a course in high school that was like pseudo programming. So it was a pseudo programming language which is in Greek with very basic instructions, like
Mhm.
and had an educational framework that you would code basic loops and very basic instructions in Greek. So I think that was my first, let's say, pseudo programming experience back then.
Mhm. So you enjoyed that back then. So you knew.
Yes, and then I went to the university to study computer engineering because, as I mentioned, I was more in the engineering side of things. So I thought that I'm going to do more hardware stuff. And the first programming language that I learned back then was Java. So
Mhm.
it was this kind of this course in the university that was called. We're using a book that's called Objects First with Java, and they were using a Blue Jay. It was
Oh yeah.
Yes. So all these course, the introduction to object-oriented programming goes through Java and the BlueJ and this book. So that was my first experience with
And you
actual.
enjoyed that or no?
Yeah, I think it was very interesting back then, and yeah. especially, yeah.
Yeah. What happens then? So you started with Java, 1990. When was it?
No,
Which
that
year?
was in 2011.
Oh, 2011. So I
Yes.
guess it was Java 8.
Yeah.
Wow. So you started with streams.
Uh,
You could use streams at least,
I could use, but it was an introductory course, but at this point, so I don't think we use streams.
Wow.
Yeah.
So you are someone who grew up with Java 8, I think. Yeah.
Yeah.
Pretty cool. So, and when you started to do something, else, so you completed a course with Plujay. Was it an assignment, university assignment, or?
It was a course that, because it was introduction to object-oriented programming back then, if I remember correctly, it was a project that was running for a full year. So you were starting doing very fundamental things like, learning all the fundamentals, class initialization, these kind of things. And then I think on the second semester, you were transitioning more advanced things, and you had to create a GUI to interact with shapes. So to create an interactive interface with some objects for different shapes and start experimenting with it. So, and that was, let's say, the final year project for first year people. So you were ending up with a Java application, and then you have a GUI that you were interacting with different shapes and different objects.
Okay, and when you started to do something else, so I mean, not only university assignment, your first fun Java program or whatever.
Yeah, for me the thing is a bit different because I did quite a big chunk of Java until while I was in my university, in my bachelor's and my master's, and then my master's I went to do an internship in a financial consulting company, and have some Java legacy code that they were running Monte Carlo simulations back then. So they had a lot of Java legacy code that they were running these kind of simulations. And
can you briefly explain what Monte Carlo simulation is? Because interesting.
So yes, what they were doing is in this company is they were doing a portfolio asset allocation and asset investment. So they were using the Monte Carlo simulation to project different investment decisions for the future. So you can imagine this can grow, let's say, exponentially. So they wanted to find out that if they have a client X and you have this amount of money to invest and you want to get retired in the 35 years from now, let's try different scenarios with different variables like different inflation rates, different asset allocation. Let's say that he's going to allocate so much in stocks, so much in bonds, so much in equity, and get different projections. So they have this tool that it would do this analysis based on the.
I still remember the Monte Carlo algorithm.
Yeah.
And
no,
how?
No, I'm not sure that I can.
Because interesting one, right? So yeah.
Yes.
And it was in Java.
That was all in Java, and that was in 2015. So it was when I was doing my master's, and they had a fun project, and they wanted someone to try to port their algorithms in OpenCL back then. So to try to run in GPUs. So this is where I did my master thesis. So I was trying to port the Java application to OpenCL and see how fast it can run the GPU.
With the Monte Carlo simulation, this one?
Exactly, yes. But you can imagine that it was back in 2015, so no one wasn't sure what we were doing exactly. So, and then
and it worked at least a little bit.
Yes, and I think after one point they kind of integrated with their product. So they, based on that, they involved it, and okay, now they have this kind of infrastructure at the backend. It's using a GPU to do this kind of.
But in your masters, so your code worked back then?
Yes, they used it. Yes, I think they published it, and we published it also in an academic paper, and then they used it for some extra, let's say, feature in the products.
This is crazy. From object first book to OpenCL migration of Monte Carlo simulation. This was like a huge progress.
it took about 5 years, so through studies and through projects. Yes, but that was my first, let's say, interaction with Java and GPUs. But okay, different concepts that compared to what we're doing right now.
Uh-huh. And was your attempt faster than pure Java, and how much faster was it? Do you remember the results?
I think back then it could be something in about in an order of magnitude like 20x, if I remember correctly,
Wow.
from the top of my head. Yes, because Monte Carlo simulation actually is one of the key benchmark for GPU compute. So if you open a benchmark suite for GPUs, most likely you're gonna step into a Monte Carlo simulation because it's in the kind of the workloads that it's extremely parallel. So you don't have any control flow and you don't have things that they cannot that they can pose bottlenecks for the GPU. So it was one of the cases that it was very straightforward porting the GPU even back then that we didn't have so much exposure on GPU compute.
Uh-huh. Okay. So that's interesting. 2015, 20 times faster. And you used JNI for that, or you used
No. It was a completely C++ standalone application. So the idea was to port the computation from Java to C++ and offload it to the GPU through OpenCL. And then they were using the C++
I thought you
applications for
access
that.
from Java, because to
No.
access from Java OpenCL, you usually would use, how to call it, a memory map buffers or some or
Yeah. No. It was a clone of the project in C++.
So you ported Java to C++ to make it work, right?
Exactly. Yes.
Okay. And what happened afterwards? So
So afterwards, I finished my masters, and then I did a break from Java stuff, and I went to work in a hardware company because I thought, okay, this is it with Java. I like what I did with the GPU, so I did a break and I went to work for Huawei. So I went there and worked on GPU hardware stuff, more CUDA, OpenCL, for almost a year. And I thought, okay, I'm done with Java and I'm gonna continue working in hardware. And then after that, I ended up in Manchester, and I found this project description online that they were saying we want someone to understand from GPUs, to understand Java, and we have this PhD project. So that's how I found myself in Manchester in 2017, working in Tornado.
this was the fastest introduction ever, I guess. So it's cool. Because you started with Java 8.
Yeah. Well, I think people at my age, they experience things a bit differently because, we didn't have so much, things that were moving so fast because I started university in 2011. So you can imagine that things from 2011 to 2015 and then 2015 to 2020, things that were working in a much different pace.
Mm-hmm.
Also, for people in my generation, you had accessing resources much more. So, it sounds like big knowledge gaps, but, the information was there and it was very easy to do this kind of steps, I think.
Yeah, cool. And you worked for Huawei, and then you found accidentally the Tornado?
No, I was looking for PhDs back then, and I was looking online, so I didn't know anything. So I was searching some websites that had advertisements, and I saw an advertisement from the University of Manchester that I was looking for someone to work in a PhD, and they were asking for someone who did GPU compute back then. But I didn't have any experience from compilers and the internals of the JVM, any of these kind of things.
So what is your first task? So how you started in the project?
I think when I started in 2017, it was just when the previous guy worked in Tornado, built Tornado, he graduated. So I think that the first task that I did was to write unit tests for for some time. I was just writing unit tests, trying to see what's going on there.
Which is, I think, a good start, right?
Yeah, exactly, yes. Because also it was a very big logical gap because, going from Java to OpenCL in 2017, it was a very big mental gap to understand what the system does. So I think, yes, that was the main task that I did back then, to get familiar with the framework and what it does.
Okay. And and what was your, I would say, trajectory from back then, from unit tests now to,
Well, for me, it was not a linear transaction, because I did my PhD on Tornado, so I worked in different things. And after I graduated, I went to the industry to work for 2 years. So I went to an AI startup. And yes, so I spent most of the time that I worked in Tornado. I worked in
But you
FPGA.
worked from 2017 to now just on Tornado, right?
No, I worked from 2017 to 2021, where I did my PhD. And then from 2021 to 2023, for a bit more than 2 years, I worked in a startup that they were doing AI accelerators and compilers for AI. And then I came back in Tornado just in time to.
Was it Grok?
It called Octo AI.
Okay.
That now has been acquired by NVIDIA, so they're doing these kind of things in NVIDIA. So I just came back in Tornado just in time to get all this, AI knowledge that I got, and try to do it in Tornado.
Yeah, super interesting, actually.
Yeah.
So and the startup, you try to build an ASIC for inference?
No, we were doing software. So because when I was working in Tornado, so I worked in different parts. I worked in FPGA integration. I worked in Graal compiler, extending the compiler for different optimizations. I worked a bit in runtime, so I had a bit, a top-down view of the stack. So when I was looking for jobs after graduating from my PhD, I found this AI startup that they were doing compilers for AI. So the idea for them, it was to be able to use any kind of libraries that you have online, like TensorFlow, PyTorch. Back then, that was the main thing, or Onyx, and compile, import operators from the library, and compile their own code into PTX, could highly optimize for specific hardware. That was the idea. So conceptually, things that we did in Tornado, they made sense, as an idea, as going from a high-level abstraction to optimizing the code. So that's what they were doing in 2021. But in 2021, when I started, then it wasn't this frenzy about LLMs. So we were mostly working for applications like for computer vision, or things like BERT, these kind of things, object detection, not LLMs.
So what I understand is, so if you have a trained model, it is available via Onyx or other platform or frameworks. And what you try to do is to generate, basically, how to call it, to cross or to translate the model into fast C code, right? So it was like a code generator from the to create an application from the weights and accessing the Onyx and hard code it in a C, right?
Exactly, but it's what we discussed about, before, about Java and about big logical gaps in this decade. So even if we're discussing about 2020 and 21, which doesn't feel that long ago, back then many things that you get out of the shelf now when you run inference, like the kind of optimizations, how you can get a model and how you can optimize this model for GPUs, they weren't standard back then. So we're experimenting, and many of the things that are standard now, we're doing just manually or writing optimization. So you can imagine that if you have, let's say, a neural network, a model for a neural network, so you would import this to our software stack and then try to do some static analysis on the model, what kind of operations you have. Like, for example, you had a matrix multiplication followed by a scale, and then you have the compiler say, okay, these two things can be grouped well together. So rewrite it to generate as one method, as one kernel, and generate CUDA code for it, generate metal, generate PTX, whatever, and run it on the GPU. And then, we're trying to fuse as many. That was one of the main things that we're working back then, how you can fuse efficiently the whole, let's say, model into smaller chunks. So to avoid having too much context switching, to avoid having too much I/O with the GPU, to having too much I/O with the memory. So that was one of the main things that they were working. And this project was called Apache TVM, so it was open source. And because it was the only, let's say, open source compiling runtime for machine learning workloads, it had a very, very vibrant community, people that were doing contribution, they were asking questions, they would try to use it in different hardware, so the iterations were very fast. So yes, so that's how I ended up working in AI back then.
So from my understanding, so if you have Onyx, it allows you to access the model, the weights indirectly.
Yes, but Onyx, that's indeed. But what happened with Onyx? Onyx started as a different thing. So I think Onyx started as a specification because as a specification for the model. So you could, but you don't see that anymore. You don't see Onyx models, right? I see that you do some. You have experience with Hugging Face, but you don't see Onyx format models anymore, right? What Onyx tried back then it was to have a universal specification for the models and to export it in Onyx and build that. And then they evolved Onyx and it became a runtime and then it became an execution engine. So they built the Onyx to run in GPUs. But how it started, it was like a specification for the model, a universal, let's say, specification for the model. So many companies, okay, it doesn't feel that bad, but 5 years ago they were trying to have Onyx importers. So to support that, we need to be able to load more Onyx. But then, people moved into other formats after that, like safe tensors, GGUF, ZML, and this kind of thing.
And why they moved from Onyx away to safe tensors? Was it like less efficient, or
To be honest, I don't know. It's something that I missed. I think I missed how this transition happened from Onyx. But back then, Onyx along with PyTorch was the most, let's say, dominated model specifications.
So, and your startup tried to access Onyx only and learn from Onyx and write high-low?
No, because the idea of what happens with them is we have an online service. So you can imagine that the clients that would drag and drop their model, okay, and our service, it would take the model and try to optimize it for different hardwares and different hardware vendors, different online, let's say, cloud providers. So imagine that you have a model and you want to run it in Azure or in AWS. You could drag and drop the model and say, I want to run it in Azure. This is the kind of things that I have. And the compiler infrastructure and runtime, it would try to optimize it for the given, let's say, specification that you give. Or if you didn't give a specification, it would try to optimize it for different hardware, like run on NVIDIA GPUs, AMD GPUs, and it's going to give you a report. It's okay. This model, if we optimize it, you can run it in this machine and achieve this kind of performance. You can run it in this GPU, you can achieve this performance. So then for you can do some, let's say, cost analysis. Say, okay, I want to run it for 1 hour per day. It would cost me X amount in AWS. I want to run it for a different amount of time in Azure, and it's going to cost me different. So that was the business idea behind the optimization, because otherwise it's difficult from a startup perspective to sell optimization compilers standalone thing.
This was a good idea. But which format was the input in your case? So
I think after one point, because it was mostly importing stuff, so I think we're supporting Onyx, Python, safe tensors, and
yeah. And what? Okay, then you have the model, but how you could understand, how to perform the optimizations? Because not that easy, right? You had to understand the model a bit in order.
Yes, but it's a different. So it's different because I think many people now they've been exposed to working with LLMs, and working with Meta Llama format. So in this kind of models, you have embedded the model also the computation side. So you would know that in the sense of Llama, so what you see in the inference, so it would be embedded in the model. So you would know that the model it has let's say a chain of 3 matrix multiplications plus a scaling plus a reordering. So from the model you would export the format of the operation. So then in the compiler level it's just a graph. So you know that these weights they go through this, and then you know how to optimize the operations and how you can optimize the data layout, these kind of things. But all this information was embedded in the model. So the inference of the model, it was closely coupled to the model itself.
In all the information is the same in all model formats? I mean, because it has to be there, but is encoded differently, or?
Yes. So you have different importers, same things like what you're doing right now for the LLMs, for example.
Mm-hmm. Yeah. Okay. And then it was bought by NVIDIA, and then you are back at Tornado.
Yes, and I had and with all this kind of transition to AI, the kind of experience that I had with Tornado and the experience I had with AI, it makes sense.
Mm-hmm.
So I started working with Tornado again, and I worked in different things on the compiler, Graal, and up to the point that ChatGPT came out, and then we had the first implementations like in Java, like Llama 2.java. So suddenly the experience that I had before, it makes sense. So I started working and discussing with the rest of my colleagues how we can improve Tornado and how we can make it more robust for work in machine learning. And I was discussing a lot with Alfonso. It's been, I think, here in the podcast a few times because he was very keen how in his implementations of the Llama 2 back then, how we can enable Tornado. So we had the first prototype of getting the Llama 2.java that Alfonso did and import Tornado. And back then our goal it was to be a very lightweight integration. So we did what you can imagine, we profile it, we found out that matrix vector multiplications were the bottleneck. So we just tried initially to import Tornado and just try to float one by one the matrix multiplication to see how it behaves. And we had the DevOps talk last year about that. And we found out that the performance it was very promising. Just by floating one of the matrix multiplications, we would see some speedup to then. So after that, Llama 3 came out and start working how to make Tornado more, let's say, robust for doing that as a whole. And we ended up releasing last month the GPU Llama 3.java, which is, let's say, a mirror version of the Llama 3. It supports Java that Alfonso did. It supports same model, same input types, but all the inference, it runs in Tornado. So you are expressing the inference part, the kernel, the computation in Tornado API, and everything happens in the GPU. So like one would write pure CUDA code, but in Java. And the initial results that we got are very promising. For at least for NVIDIA GPUs, we would see like even 120 tokens per second for 7 billion models. And last week we released Mistral, so now we run also Mistral, the 7 billions. In some initial benchmarks that we did compared to Java, we are about 6 times faster. And so yes,
but it's still Tornado is Java, so into pure Java you see, so SIMD, right?
Exactly. Yes. So I think that's the main thing, and because once someone is diving into the source code and see that it's just Java, the way that we're expressing the computation and the way that we're offloading the inference onto the GPU is still Java. It's like using any other library that just takes care of it. I think this is it, and I think now people that it works and the performances in that level, I think people they start thinking, okay, it's pure Java, so I can do more things. Maybe I want to do some pre-processing in my weights. So maybe I want to, let's say, load the model, then I have the weights, and maybe I want to do something that it's special for my use case to, let's say, scale the weights or try to do things, and you can do it on the GPU directly with the Tornado API. So I think it was a very good exercise for us as a team, that how to make Tornado more mature and import it into the Llama 3, how it can actually be used in actual services from people.
What Alfonso did in Llama 2 Java and Llama 3 Java, so if you look at the code, so you will see that it loads the weights, and then he has the calculations, the matrix multiplications with SIMD. And this is what you referred earlier, right? The matrix calculations would be a part of the older Onyx or PyTorch or Safe Tensors model, right? So this is what
exactly they would be how they call them. It would be operators. So when you see a matrix vector, you would have an operator that it does a matrix to vector multiplication for floats. You have an operator that it does the same thing with doublets. You have an operator that it does the same thing with FP16, etc. And then you have the compiler and say, I have two matrix multiplications together. They have the same read-only weight. So what I can do is that instead of having two different operators and having two different function calls, I can merge them into one kernel. So I'm gonna load the read-only data just once. So this is the kind of optimization that one would do in the GPU space.
So
this is what Tornado does right now.
So what the older models on the startups did, or what they were. So inside the model, the operators were just declared, and then you loaded the model, and it was interpreted in various way or compiled or whatever, right? So the files were not executed. They just said, okay, if you would like to execute me, just do this. And
exactly, because then you need to go from model to an executable for the hardware. So you need to translate the model into hardware code, into CUDA, for example, it's OpenCL.
So all the models are containing weights and the operators, or because what I thought is that some models is just the flows basically, and the inference engine already knows what to do.
Exactly, that's different. So for the LLMs now, you just have the weights because you have a standard. Because you have a standard, let's say, inference architecture. So you have what it's been inside the forward method, and this is a standard inference. But for the other kind of models, you have the inference, let's say, specification embedded in the model.
Now I understood this, because it was for me always hard to understand. So in the dark ages, so 4 years ago, all the inference was specific to the model. There was no standard.
Exactly.
And now with the rise,
now you have very small at least for LLMs, because now what we are working for the GPU Llama 3 is that, as I mentioned, we released Mistral last week, and now we are working on releasing a Gwen 3 and DeepSeek. So you have very small permutations between inference. So in this kind of LLM, so there's a very small difference in the actual inference implementation between the models. So, for example, Llama 3 and Mistral are identical. So all the computation is identical, and going from
so identical means if I have Llama 3. Sorry, what I had from I had a quantized model from Alfonso for Llama. So I would also work with quantized model from Mistral, right? So it would be no
exactly.
No
so
changes.
The inference is going to be the same. So the sequence of operators, the sequence of algorithmically, the sequence of mathematical operators that you're doing, they're exactly the same. So you might operate in different weights, the weights are different, but the sequence and the computation is identical. And what is changing is, first, now that we're working in Gwen, there's a small, let's say, difference between the inference that works for this to Gwen, but it's very small. So you imagine that you have a set, let's say, a sequence of operators. Say, I'm gonna do a matrix multiplication, and then I'm gonna do a scale, and then I'm gonna do a NAT. And the only difference now is that Gwen has some additional normalization layers. So what they call is normalization. So from the output of the one computation, you just go through the output and you apply a factor that's already loaded in the model. So
you know why they did it?
Not really, because I think it's how they train the model and about the internals of the model. But
Okay.
it's very small difference, and it's just an extra core. It doesn't change anything fundamental.
Okay, so you means what you're doing right now, I guess you are hard coding or you're building like small adapters for the adjustments to be able to read all models similar to Llama, right?
Yeah, but on the same time, we try to refactor to make it in a way that can be easily extended. So we wanted to look like a library in the future, not like a one-off inference engine per model. We want to have it like in a modular way that if someone, let's say that you are a machine learning expert, okay, and you want to do another permutation of a model like Mistral, Llama, Gwen, Gemma, whatever, and you know how to express the computation, we want Tornado to be able to have for you to have access in the building blocks. So what I mentioned right now, that the difference between Llama and Gwen 3 is just an extra normalization layer, which for us is an extra call to a Tornado kernel. We want the end user to be able to have access to this kernel from Tornado and just say, okay, I just want here to have an extra call in this kind of computation, and it's gonna work. So we want people that they use Java and they do this kind of development, and they found that JLlama or Llama 3 works for them, to be able to use the Tornado building blocks to do prototyping fast. So no need to do, if it's something minor that you don't need, no need to use PyTorch or something else.
So I think the Llama project, so from Meta on Facebook, they started the standardization, right? Because they open source the model. So this is why Mistral is also similar to Llama and all the others. Without Llama, there will be no standardization. So we will, right? So we'll be still forced to use Onyx or whatever with the operators because there will be no standard. So and Llama became a standard, and this is why we can do this, right?
Yeah, and I think now that you mentioned standardization, I think it's what has been missing from the JVM ecosystem right now, because you've seen there's the JLlama project. People are actually using that Llama 3 Alphonsus. They've integrated with JLlama, with Langchain4j, for example, and now our project that enables the GPU. But one of the key things of this model is that the data types, and one of the fundamental aspects is that you need to be able to do things in lower precision, and like FP16 half floating point, Q4, Q8. But okay, we don't have this kind of types in the JVM. Or what people they are doing now is that they emulate them with byte arrays, and which is something very rare prone. And if you do something, if you commit to do it with, let's say, one framework, then you are bound to it. So you cannot get your inference and try to do it in a different, let's say, framework. So I think we miss a bit of standardization in the JVM ecosystem right now, at least for the types and how we import the models, for example. It would be crucial because
Valhalla project might help, right? So if we had,
Yes, and it's something that we're exploring in Tornado because already we moved into Panama a couple of years ago. So now all of our Tornado types are using memory segments underneath. So
you need FFM, right? So this,
yes.
foreign function memory.
Yes. So yes, I think Valhalla and having some depths about potential data types for at least, let's say, FP16 precision, it would be great for now.
FP16 I think is already part of JDK. We have half floats.
Yes, but I don't think that it has native support, if I'm not mistaken.
Okay, this I don't know. I just know it exists. And okay, so that's interesting discussion. So Llama standardized everything, so it allowed us that Llama is just, if you download Llama, this is GGUF standard, I think, right? GGUF. Yeah. This is just if you open this is just bag of numbers. There are no operators there.
Exactly, it's about
But you have to know that the GGUF is, let's say, DeepSeek or Llama or Mistral, and then you have to know that this model has specific, how to call it, adjustments, right? So you have to perform it.
Yes, because you have a metadata that is associated with the model. Because you need to know when you are parsing the model, how you're going to parse it. Because you need to access metadata that, because inside the model there is embedded information like the number of layers, the number of heads, the number of weights, some constant factors. So these kind of things you need to import them before parsing the actual data for the weights. And this is helpful also for the inference, because when you are running the inference and you are doing things like the multi-headed attention and these kind of things, is based on the configuration that you have imported from the model already.
So there's the GGUF ships with a metadata header or whatever, right? So you have to read first and then learn from that and configure your inference engine.
Exactly. Yeah, exactly. Because what we mentioned before is that while the inference is the same, you need to have this kind of parameters in order to be able to work for the different models. Right?
Okay.
And
so now
I think it's good because it's embedded everything in the GGUF models, so it's much easier to standardize it and having it's a library in Java that you just parse the GGUF and with a specific format.
Can we say that all major models ship now with Llama format, the GGUF?
I think in the high-geeking phase, all the models that are for LLMs, you most likely you're gonna find it in GGUF.
That's interesting. I knew that it's almost a standard, but it seems like it became a quasi-standard. Right?
Again, if I'm not mistaken, my sense from looking at the projects, like because Llama C++ kind of dominates the local inference and it's for them the GGUF support is a first-class citizen. It's kind of became like this because all Llama other engines they just use Llama C++ on the backend.
Okay. And all Llama projects ship with GGUF format, right?
It depends. I think
Mistral, for instance.
Mistral, yes, has GGUF.
Yeah, on the DeepSeek.
Yeah, I think yes.
And Gwen,
Gwen, yes.
Yeah, there's also Microsoft Phi, or so you
it's the Phi 2, yes, and the Gemma from Google.
Yeah, this is I would say, serious standard, right? I mean, all major models are shipping with GGUF. Okay, so this is great news. So what we learned is with the new version of TornadoVM, we are able to read GGUF, which is a derivation of Llama, and you are adjusting now the engine to understand more and more models, and you are able to be 20 times faster, optimal cases, than Llama 3 Java, right?
Not 20. For Mistral, we are 6.
6 times?
Yes. And for Llama 3, for FP16 right now, on NVIDIA GPUs on the 5090, we are 3 times faster.
Okay, sorry, 20 was the Monte Carlo simulation. I had the 20 in my head, so sorry.
No worries.
Yeah, but I mean, 3 times is crazy. So with Llama 3 Java on my machine, I think I had...
Exactly. So I think this why it's great what Alfonso did with Llama 3, because he did it in a compact way in a single file. That for us, what we did with GPU Llama is just a plugin replacement. So someone who's actually using in his project Llama 3 and it makes sense, they can just clone a repo, clone it, and it's the same thing.
Yeah, but already with Alfonso's Llama 3 Java on my machine, I had 10 tokens per second. And if you have 10 tokens per second, it looks already okay. So, you get...
Yes. We have some examples. I think we have in one of the GIFs, I don't know if it's the highest performance. So in the 1590 that we are using for testing, we achieved 120 tokens per second for a 3 billion model, which is crazy.
But this is 12 times faster.
No, because I don't think that Alfonso's Llama, because, okay, the main thing is which model you are testing, in which format. So that's why you get 10 tokens per second in your machine, but what kind of machine is it?
I had the MacBook Pro on Apple.
Yeah, so I think for Intel, if it's an i9 with hyper-threading and this kind of things, this number most likely is going to be a bit higher than that.
Oh, i9 without GPU, you mean?
i9, no, it's CPU, an i9 CPU. Most likely, I think because of the vector API and these kind of things, most likely the performance will be.
But Mac has the unified memory. I think this is the huge difference, right?
Yes, for the CPUs.
Exactly.
Yeah. Yes, but I'm not sure about that. But I think on Alfonso's Llama 3, I'm not. The vectorization doesn't work that. The performance vectorization on Arch 64 is not that great as.
So the last time I chatted with Alfonso, so my MacBook my Apple MacBook Pro was faster than his brutal machine, or at least similar performance. So he had a real workstation on Windows, and on with his code, mine was almost as fast or even faster than his machine. So with SIMD, just no GPU, right? So this the SIMD, and I tried with Tornado, and it was similar performance. So this was not a huge impact. So I created an issue.
Yes, I think I replied to your issue. The thing with MacBooks is for us to work in MacBook, we use an OpenCL backend. Okay, so we generate OpenCL code and run it on the MacBook. Functionally, it works the same way that what we're doing for NVIDIA GPUs, for example. But what's happening with OpenCL and MacBook is that the OpenCL has been deprecated in MacBooks for quite some time. So if you're familiar with MacBook, the way to do shading stuff like graphics, they use the proprietary programming which is called Metal. So because we had this experience and the way that we generate OpenCL code, it should be performant for an parallel architecture like the M Silicon GPUs. But because OpenCL is deprecated in Mac, I think their drivers, they've been stuck into an old version, so they don't do so much aggressive optimization and stuff in OpenCL. That's why the performance is that. So we made a decision when we released the GPU Llama, and we said, okay, because it works on Mac, let's release it like this with a notice that the performance is not great.
I thought you noticed this. I just created the issue just to inform you, right?
Yeah. Because we know that. So if someone wants to actually use it in production, they can just do the development locally, even if performance is not great.
Yeah.
And then they can deploy it in a server that has an NVIDIA GPU and get this 6x, 5x, by just run it. So it's good to have it as a feature, so you can do your local development for your model in your MacBook, and then once you want to deploy on the cloud and they have more high-end NVIDIA GPUs, you see the performance bumps that we're showcasing. But now we are starting a project that we're going to start developing a Metal backend from Tornado. So now we are going to go directly from Java to Metal as well. So we expect that, when this is done, to be able to have much better performance on MC.
This is excellent news because what I already saw, there are lots of enthusiasts which are running the Mac Minis. These are cheaper Mac Minis for inference, and they are cheap and very fast, and also energy efficient. And what also surprising news that there is a Swift and Java integration right now since WWDC. So they maybe will help or not. So you could also look on that. Okay, but more specific to your work now. So this is out. So I tried it. It worked. What I was surprised that I have to install Python in order to run the project. So why?
Yes. Okay. This because we want it to be very simple, and the only thing you need Python is because we have this runner script that is called the Llama Tornado. Because the script is written in Python. That's the only way. That's the only need you.
Is it so complex a script?
Not really, but just I personally did for simplicity. But if you scroll down on the bottom of our page, the GitHub repo, we have a section that it has just the Java command. So
okay, this was not clear for me because I try to do one by one whatever you said and to get the full experience. So my feedback would be, what I like, I also contributed a trivial commit to Alfonso code is to make the script runnable without compilation, just Java and do this, right? So I could run Java Llama, and Tornado is a little bit more complicated, but it doesn't have to. So I would say the developer experience with Llama was that great that at the DevOps conference, the attendees asked me, I think 3 times in a row, what you did is impossible. This was so simple. And what I will do is to update the tutorial or this README, or have two READMEs, and one should be as simple as from Alfonso. Sorry. Of course, you have to install Tornado first. So this, but for instance, Python for me it is brutal because I had really bad experiences with Python. I saw this already. I was like, okay, oh man, this is so. I would push Python as far away as possible for pure Java project, because you started, I think, Alfonso's code, and this was just genius. Java, Llama 3 Java, and it runs. No compilation, nothing. And this would be actually stellar if this would be. I think it is possible. So there's because
Yes, I think. Let me check. There is a section the repo that called easy integration, and there is a pop-up window, and it has just the Java command.
Perfect.
And
make it more prominent. So for me, it was too late. I started already with the sequence, and then was too late because I said, okay. Then I was, it's okay. We just do this and see.
Okay, I will try to adapt. But I think how we thought it with a Python script, it would be to be that easy, and because the thing is that if you need to run with Tornado, okay, just your Java command, but you need to pass some things like the module paths and these kind of things, and it can be a bit too populated for someone to.
This is, I think, for Java programmers, they would prefer a brutal, arguments list for Java than Python installation. And another thing which I can give you feedback, what immediately happens for me in production is we have to run in kind of CI/CD pipeline, whatever. And for that, I will have to install Python, automatically. And if
that makes sense, to be honest. Yes, I think we mostly thought about it for simplicity, just having.
This is I'm a Java developer for me, and lots of Java developers don't like Python. So optional, cool as optional, but I wouldn't do this mandatory. And even you could do such a script with Java, or there's an excellent tool, JBank. I also try to avoid JBank. Because why I need JBank if you can just start Java? But in your case, I would prefer JBank over Python, right?
Yeah, I think, I agree with your feedback, and it's where we stand right now. And
it's just marketing, what I tell you, right? This is just everything works, and for me, it's just a different packaging. Yes, but I tell you, the packaging is very important. So if you go to conference and we saw, two-liners, everyone says crazy. But if they see Python, they're okay. Because people don't like it, because maybe they don't want to deal with LLMs, and they will see this and they say, okay, this is crap, way too complicated, right? Yeah. This will be the first feedback. So this is...
that's why last week we have someone working in our team on integrating Tornado with SDK Man.
Uh-huh.
So this is one of the things that I think is aligned with what you're saying right now. So we try to push Tornado into SDK Man, so even to make that step that easier. So
super cool. And even better,
use daily SDK Man for.
And even better would be just use Java 21, nothing else, and this is the parameter list, because, and this is, I'm also happy because then it is maintainable, because everyone understands no dependencies, just this what you need, right?
Yeah.
Because the Tornado, I was already afraid of the Python, and the Tornado installation was very easy. There was nothing, as I remember. This was like, not even, so for me, the biggest part was the Python installation with the virtual environment. And everything else was simple. Okay, what we didn't mention at all, what you actually did, what was the optimization and how it worked?
Yes, so what we did is that to make it work and be that fast, we are doing two different kinds of optimizations. So one, it's a runtime optimization, the other is a compiler optimization. So as I mentioned in the past, things that I did in that AI startup, they make sense. So if one goes and tries to look into the inference and the kernels, we do a lot of clever things that you're gonna see it in a GPU library, like fusing computation together. And
one question, I will interrupt you. Is it enough material to cover in another podcast?
It's very technical and very GPU oriented. I don't know if people
because the approach would be interesting, and maybe
yes. I think in a nutshell, for someone it would be interesting if they open the inference engine that in GPU Llama and they have experience from GPU and they look into it. they're going to see Java code and they say, okay, I understand what I look. But it's also it's going to make sense for someone who's a Java developer because it's just primitive, so just add additions, multiplication, just doing stuff on the array. So that was the main thing. And in terms of runtime, we extended Tornado with the ability, let's say, what we call it is consume and persist API. So I don't know if you have seen Tornado that have this concept of
on the last podcast. What I learned is what you can do right now is to have a like kind of a singleton, so that you can remember the data between calls. And back then it was not possible, so you lost lots of performance because you had to call the kernel over and over again, right?
Exactly. So this is the consume, let's say, and persist API that we introduced. And for us, it was very interesting experience importing the Llama 3 for Tornado because we thought a bit more about this kind of concepts, how we can, try to optimize our data transfers. And also we developed 2 different tools for profiling Tornado that we plan to release the next weeks. So we have visualizers that visualize the Tornado bytecode. So you can use this and understand what's happening under the hood in Tornado. So these are the main optimizations that we did, mostly to optimize the data transfers from the runtime side of things. So we don't do any excess I/O with the GPU. We just copy what needs to be copied. We copy all the weights when you start the inference, so you don't pay this kind of penalty. And then we optimize the kernels in the same manner that one would do for a GPU framework that does inference.
I think it's too interesting. I will have to invite you again. If you don't talk, about low-level GPUs, at least there were tools releases because it seems like the development of Tornado speeds up right now. So it is an interesting ecosystem.
I think right now things are moving very fast, and we plan to have releases every week or every other week with importers or performance or the tools, all this kind of knowledge that we gain by doing this port. I think yes. But
so
the main thing is that
what could be perfect? Maybe a good idea is to introduce the high-level concepts like the persistence consumer API you said, right? Yeah. And where to look at the code. So if someone's interested, could help just to look at the Tornado code or whatever, and what it is and what else you can do. Maybe if you can reveal, okay, we can optimize in this direction, and how much potential Java has for inference. This would be also interesting part, right?
Yes, yeah, that would be interesting. But I think one of the biggest announcements that we're gonna do is we're creating a demo with integration with LangChain4j that I think people are going to find it useful if they want to enable it.
In my project, it's very useful because all my project are Quarkus and LangChain4j is also interesting. And maybe one final question. So if you compare the performance of Python and Java, if it's comparable, is what you will say? It's you will do similar stuff with Python inference or Java. So
if you want to do pure Java inference, I mean, without the GPU, or if you want to use the Python as a...
No, I would say you could write TornadoVM in Python, right? So it would be similar concept, I would say.
I think I would stick with now. I think with all the latest advancements and all the pieces that they come together, like Panama, Valhalla, I would stick for the JVM. I think yes, and I think this is the right time to do this kind.
This is also my impression. This is why I'm asking you, because you are way deeper than I am. I just have a higher level view, and my intuition is, with GraalVM, TornadoVM, Babylon, Valhalla, and there's like a perfect storm, and Java could become, the really interesting inference engine, efficient one. And even years ago, there was a DJL framework from Amazon. So, and what they did is they used that for inference, Java, not Python, because of multi-threading. For instance, multi-threading and stuff like that is way easier in Java. And yeah, pretty cool. So where people can find you on the internet?
Yes, in my GitHub or Twitter, I have the same username. It's called Mike Papadim. I've been having this for many years. So yes.
Okay, was really interesting, and yeah, and I'm really glad that Tornado takes off right now. So yeah.
Thank you.
See you next time.